All right, today we're going to talk about something really cool. A chemical tool so powerful, you can almost call it a master builder for chemists. We're diving into the Grignard Reagent.
I mean, think about it for a second. How do you actually build a molecule, right? How do you take these simple little pieces and just snap them together to create something bigger, something more complex, maybe something incredibly useful? Well, for more than 100 years, one of the very best answers to that question has been the star of our show today.
And look, that's not just me hyping it up. This thing is often called one of the most powerful and versatile tools in organic chemistry. Seriously, this isn't just some other compound sitting in a flask. It's a total titan of the field. It's the go-to when you need to forge those carbon-carbon bonds, which, are the very backbone of, well, pretty much all of organic life and industry.
And this isn't some newfound appreciation either. The genius of this discovery was spotted almost right away. A French chemist, Victor Grignard, figured this out around 1900, and by 1912, boom, he was awarded the Nobel Prize in Chemistry for it. That's just how much of a game-changer this was.
Okay, so what is it that makes this reagent so special? What's the secret sauce behind its incredible building power? Let's get into it. The whole secret, it's all in the bond.
So at its core, this is a Grignard reagent. It's called an organomagnesium halide. Yeah, that sounds a little complicated, I know. But this general formula, R, M, G, X, it gives us a perfect little roadmap of what's inside.
Let's just quickly break that down. The R there, that's some kind of carbon-based group. Could be an alkyl, vinyl, or aero group. Basically, it's the chunk of carbon we want to add to something else. Then you've got Mg, that's a magnesium atom, simple enough. And X is a halide, which is usually going to be chlorine or bromine.
Okay, now this is where the magic happens. It's all about that bond between the carbon and the magnesium. You can picture it like a chemical tug-of-war for electrons, but it's a totally rigged fight. Carbon is way more electronegative, which is just a fancy way of saying it pulls those shared electrons a lot harder than magnesium does.
And this is the whole key right here. Because carbon wins that tug-of-war, it ends up with a partial negative charge. This completely flips its normal chemical personality on its head. It turns that carbon atom into the super potent attacker, what a chemist would call a strong nucleophile, and it's just itching to go find some positive charge and form a brand new bond.
So we get why it's so powerful, but how do you actually cook one up in the lab? Let's take a look at the recipe.
The way you make it is actually surprisingly elegant. You start with something called an organohalide. That's your R group already attached to a halide, X, and you just react it with some magnesium metal. But this whole thing has to be done in a very special solvent, which turns out to be a key player all on its own.
Right, that solvent is pretty much always an ether. And the ether is doing a whole lot more than just dissolving everything. Its oxygen atoms actually cozy up to the magnesium atom, kind of like a chemical bodyguard. This stabilizes the whole reagent, which is super reactive and just keeps it ready for action.
Okay, when you're making this super reagent, there is one critical rule, one absolute law of the lab that you absolutely cannot break. You have got to keep everything completely dry.
And here's why that's so important. Water is basically the Grignard reagent's kryptonite. It is so incredibly reactive, so eager to do its job, that if it bumps into even a tiny trace of water, it'll react instantly. That powerful carbon-magnesium bond just gets shattered, the reagent is destroyed, and poof, your whole experiment is ruined. Okay, so we have forged our powerful tool, and we've protected it from its one and only weakness. Now for the really fun part. Let's put this master builder to work and see what it can actually build.
So the main job for a Grignard reagent is to go on the attack. Its target? A carbonyl group. That's a carbon double bonded to an oxygen. Its whole purpose is to smash one of those bonds and forge a brand new, rock-solid carbon-to-carbon connection. I mean, this is molecular construction, pure and simple.
And the amazing thing is just how predictable and precise this whole process is. If your Grignard reagent attacks methanol, you get a primary alcohol, every time. If it attacks any other aldehyde, you get a secondary alcohol. And if you point it at a ketone, you build a more complex tertiary alcohol. It's like having a perfect blueprint for building exactly the molecule you're aiming for. But wait, there's more. This master builder is super versatile. If you react it with something different, not an aldehyde or a ketone, but with carbon dioxide, and you can literally just bubble CO2 gas through your solution, or even toss in some dry ice, it does a completely different kind of magic. It creates a carboxylic acid, which is another incredibly important class of molecules.
So, let's wrap this up. What are the big takeaways? The Grignard reagent is a powerful carbon attacker, all thanks to that polarized carbon-magnesium bond. You make it from an organohalide and magnesium, but you have to do it in super dry ether. Water is its one major weakness, its kryptonite. And its main job? Building different kinds of alcohols from aldehydes and ketones. But it can also build carboxylic acids from CO2. It is, without a doubt, an absolute cornerstone of synthetic chemistry.
You know, the Grignard reagent totally changed the game for what was possible in a chemistry lab over 100 years ago. It really makes you wonder, as our understanding of the world gets deeper and our tools get even sharper, what's the next great master builder of chemistry going to look like? What new molecular doors are we about to unlock?